Hope everyone had a good weekend. Okay, so remember last time we were looking at these Riemann surfaces X, and so far we've introduced a number of different objects on the Riemann surface and sort of discussed some of their properties. Right. So the first thing we looked at was these sort of meromorphic functions. And then last time we also looked at these, right, so these were holomorphic maps to S2. And the other thing we recently looked at was this notion of a holomorphic one form. Right, so we had omega, which was a complex of 1,0 form on X, and it was holomorphic, so the del bar of omega was 0. This is holomorphic one forms. And I mean, we were interested in these things because, on the one hand, I mean, they're natural things to look at, but on the other hand, we were sort of interested in understanding sort of two questions, which is, the first question is, can we ensure some non-trivial and then the sort of second question is if they, that's sort of the first question. The second question is sort of if we have these guys, can we say something about them? Can we, if they exist, how many are there? And what properties do they have? Okay, so, I mean, as we saw, this is a somewhat non-trivial exercise. So, for example, one of your homework problems, or one of your exercises, which we'll see how to show this kind of more, I mean, we'll give another way of showing this that sort of maybe explains it a little bit better, is that if you have X as the Riemann sphere, then there's no holomorphic one form. Okay, so that means that certainly there's something we need to do here to sort of say why we have the existence of this thing. The other thing is, of course, we know some things about their properties. So, for instance, we showed a while ago that if you had Q such a meromorphic map, and it had one simple pole, then X had to be the Riemann sphere. So what that means is if you had X having not being the Riemann sphere, but being closed, say, then it has to, I mean, we can't ensure the existence of a meromorphic map with just one simple pole. We have to have, if there is a meromorphic map at all, it has to have more than one pole. And so the point is, these are sort of related to the underlying topology, and are going to be crucial in sort of understanding. I mean, they're crucial in using Riemann surfaces to be able to answer these questions. Okay, so. Right, so since the topology seems to play a role, I mean, we introduced this this splitting, right, of the right, and we already saw that this D operator, which gave us de Rham cohomology, was closely linked to the topology of the underlying surface. So it'd be interesting to see if there's some analog with these new operators. Of course, I mean, this is just an invariant of the surface, whereas this obviously uses the Riemann surface structure. So we have to be a little careful about what we're going to derive. But it turns out to be the case that we can get some interesting information. By the way, I should just a final remark, right? Right, we saw that on the Riemann sphere there was no holomorphic one form. On the other hand, you should convince yourself that, and we'll see why this is sort of that on, say, a lattice, so this torus, you definitely have 1. And not only do you have 1, but it has no zeros. And that just comes from the dz on C and the fact that that's invariant under the actions of the lattice. Okay, but going back to this, we have this splitting of the operator, and we had this diagram. So we had this the complex value functions on X, and then we had this, let's call it del 0 to the 1, 0 forms. Then we had this del bar to the 0, 1 forms. And then we had right, so I'm just putting these indices down just so we have, just for the time being. Right, and right, remember these two guys was a decomposition of the complex valued 1 forms, and so we had a kind of map D here and a map D here, and the de Rham cohomology was exactly, say the first group is exactly the quotient of the kernel of this map mod the image of this map. But we also now have this new square, so we can kind of introduce we can think of studying the sort of cohomology theory of this guy, which should somehow refine the cohomology that we got from the de Rham theory. So this is, of course, I mean, it's already interesting in the Riemann surface case, but of course it's much more interesting in general. So just to give ourselves some terminology, right? We're going to be, it's a little bit different than the case of de Rham theory, and I'll maybe discuss that in a second. But so now, given this diagram, we introduce the following groups. So we have the 0 group of X, which is just the kernel of the del bar 0, right? So this map, right? So observe this is the space of holomorphic functions on X, right? So the maps, the functions whose del bar is 0, so holomorphic functions. So similarly, we have the H10 of X, right? So this is going to be the kernel of the, so these are the holomorphic 1 forms. And then we want to introduce some additional groups which correspond to the del operations. So in this case, and these are going to be slightly less, have less clear in terms of what they represent, but let's just define them. So they're the, this is going to be equal to this is basically, if we look at the image of this guy, so we want to take this guy and mod out by the, right, this is going to be the image of this guy, but, I mean, we don't care about the image of this guy, but rather we care about how much this fails to be onto the image. So we let this be the space of 0, 1 forms mod the image. And similarly, then we let H11 of X be the space of 2 forms, complex value 2 forms mod the image of right. So here we're wondering, to what extent can we write a 0, 1 form as the del bar of a function, complex valued function. But these we don't have sort of names for in the same way we have names here. Right, so the observation here is that, of course, this is definitely distinct from the de Rham cohomology and definitely uses the complex structure of X. I mean, it is included in a very, very, very clear way, because already if we look at these sort of space of holomorphic functions, right, I mean, in the de Rham theory, this should be somehow the space of constant functions, so it should just be measuring essentially the number of components of the of the space X, whereas here it's holomorphic functions. So of course, if X is non-compact, we expect there to be lots of them, in fact, an infinite number. So this is already, so observe that, for example, if X is equal to, say, C or D, that H00 of X is infinite. But of course, if X is closed, then is essentially is closed and connected, then this is just going to be C, right? This will be the constant functions. So we see already that there's a kind of distinction. Somehow in the closed case, we get much closer to what we would sort of expect from the de Rham theory, where it's one-dimensional rather than this infinite-dimensional case. The other thing is we can also see, we're using these operators that are coming from the Riemann surface structure, so we expect that the Riemann surface structure should tell us something. So of course, in the closed case, these are all the same. But already in the open case, we can see that there's a distinction between these two, right? So you should think about this. But the fact that the D is inside of C means that we can take any holomorphic function here and just restrict it to a holomorphic function here. So that means that we get a natural map from the space of holomorphic functions of C that injects into the space of holomorphic functions of D. But of course, there's lots of holomorphic functions on D that don't arise in this way. So for instance, any function that had a pole outside of D would be in here when you restricted it to here, but would not come from here. So in this sense, the space of holomorphic functions of the disk is somehow strictly bigger than the space of holomorphic functions of the complex plane. Okay, nevertheless, as we'll see, sort of based again on this observation that somehow in the closed case, this space of holomorphic functions is very close to what you would expect from the de Rham theory. We'll see that for closed surfaces, actually this whole theory is much tamer, and though there will still be, of course, dependence on the complex structure, which I'll discuss. Okay, so we want to now make some observations about natural maps. Okay, so we're trying to understand the relationship between these various groups. So the first thing is that we can look. There exists a map sigma which takes the 0, 1 of X to the right. So the way this works is we start with a 0, 1 form omega, and then we send it to. We take its complex conjugate, right? Right. So remember, this would take in local coordinates. Say this would take dz to dz bar, and then the point is this is an equivalence class, so we have to take its class inside of here. So the second thing is we have a bilinear pairing. So bilinear pairing. B. So now let's just this is for X closed now. So as I said, somehow in the open case this is going to be a bit tricky to deal with. But so let's since we have things like this, so let's always look at the closed case, which is the interesting case for us. Okay, so we're going to have this natural pairing between the complex plane, where we take a form, say omega, and we take a class theta, and we map it to the integral over x of omega wedge theta. Okay. So the point here is that again, you should check this, but we're taking a representative of this and then integrating it. And this is independent of the choice of representative exactly by Stokes' theorem, because if we change the representative here, we'd have a D here that we could pull out and get 0. But you should convince yourself of that. Okay, so we have this bilinear pairing. Okay, we have an inclusion map I of this space of holomorphic 1 forms. Sorry, 1, 0. Into just the normal de Rham theory, but with complex coefficients. So, right, everything. I mean, when we talked about de Rham theory, we used just the real valued forms, but you could, of course, just use complex valued forms, and it doesn't change anything. It's just about tensoring with C. So we're going to include this into here, and the idea is we just take our 1 form and we just think of it, right? We know that we know that a 1 form, a holomorphic form, is automatically closed, right? So here we use that we call a 1 form, a holomorphic 1 form. Right, so since it's closed, we can take its class in the normal de Rham theory. And just to be pedantic, right? So the point is it's closed, so we can write omega is equal to, say, omega 1 plus I omega 2, where these are, say, real. And the point is they're each individually closed. So when what we mean is we're just taking the equivalence class of this guy plus I times the equivalence class of this guy. And then finally we have a map that takes H1 of X to H2 of C of X. Right, and so again, these are both quotients of the space of complex value 2 forms. Here it's by this image of this del bar, and here it's by the image of D. But the point is, and you should convince yourself of this, but the point is the image of del bar 1, if you like, is contained inside of this is the image. Is contained inside of the image of D. D1. So in other words, here we're right here we're when we take the quotient, then this should give us the well-defined map, assuming I did things correctly. Yeah, so this would be a sort of surjective map in principle. But then what the point is, right, we have all these maps, but I mean, that's great, but the upshot is that actually there is a lot more we can say about them in the closed case. Yeah, sorry. The reason I'm getting confused here is, of course, because del bar is mapping from the space of 1, 0 form. So, right, of course, the del itself doesn't do anything. So that's why we have. I mean, we have to be careful, but it's really, we're using the fact that del bar, I mean, we're using, we have to be careful. You should check this, but it's, of course, using the fact that what space our del 1 bar makes sense in. Okay, so the point is we have all these natural maps, and then we actually now can get a nice theorem which of course is which will explain using these maps how this these space of say these various groups we get over here from the complex structure relate to the theory we get from the de Rham theory. Okay, so let X be a connected, closed Riemann surface. So the map sigma induces a C-linear map between H01 of X and H10 of X with a bar. So you should think about that for just a few seconds, right? Of course, this map is not, I mean, here we just mean just apply sigma and then take bar. Okay, so that, of course, we want it to be C-linear, so that's why we need to put the bar here. Okay, so that's the first thing that's true. The second thing that's true is right, so the second thing that's true is more interesting, so the pairing B induces an isomorphism. Well, C-linear isomorphism. Obviously, map is stupid. So it induces an isomorphism, again, between okay, so these are just saying that basically these two groups are kind of the same. That's not so interesting. So the one that we really want to exploit is the following, which is that there's a natural isomorphism between H10 of X and H01 of X to just a complex H1 of X, right? So this is, of course, we mentioned last time, this should just be C to the 2G. Right, we gave a way of kind of doing this identification last time. So, I mean, we know exactly what this is, and it's just based on the underlying topological structure, and the map is actually given pretty explicitly. So let me reorder this so it's agrees with my notes. But we take a form alpha and a class theta. Is that right? No, take a class alpha, form theta. And we map it to I of alpha. Wait. Right, we map it to I of alpha, and then we add bar I of sigma inverse of the class of theta. Okay, so this is what this says is that, right, I mean, essentially, this tells us exactly that the complex dimension of this is G, and it's entirely determined by the underlying topology. So this is, of course, though, where you should see that actually the complex structure does enter in to the story, right? Because here we have this identification. So what we're really saying is our essentially one way of thinking of it is our complex structure is giving some natural splitting of this guy, right? So the point is, and one can check this, say, on the torus, that this really is the case, but you would expect that it makes, one would hope that maybe different complex structures give you different splitting. And so you can see on the level of the splitting, at least the complex structure in terms of this theory. Right, so the point is on some levels this is only determined. There's important information in this, which is the size of it, which is just given by the topology. But there's still the complex structure does still come into how this is split, which is again, if you recall how it goes back to the fact that this splitting of the one complex valued one forms right here. This was really this was the complex structure. So there's a remnant of it in this theorem. And then the final just observation, which I won't dwell on, but the map U is also an isomorphism. Okay, so the point is we want to, there's something to prove here. So I'll leave, it's relatively elementary from the following observation, which is this is going to be this is sort of the main thing we're going to focus on for the, at least when we talk, this is what we talk about tomorrow, and then use it on Wednesday to sort of give a proof of the uniformization theorem, or a generalization of this fact. And then the last 2 days, I'll just switch gears and talk about minimal surfaces and how they relate to everything we've done before. But the point is we have this, to prove this, we need the following theorem, which is highly non-trivial and uses, it's really, unlike everything we've done before, which is sort of geometric and almost kind of algebraic in a certain sense, this is really truly analytic. So the theorem is the following. So let X be a closed Riemann surface, and rho a smooth real two-form, then there exists a smooth real-valued function U with delta U equal to rho if and only if the integral over x of rho is equal to 0 and U is unique up to addition of a constant. Okay, so just to remark, which we'll of course discuss again later, so this condition here that the integral be 0 is clearly necessary just by Stokes' theorem, so you should convince yourself of that. Similarly, the fact that this U is unique up to an addition of a constant is a relatively straightforward fact, consequence of the fact that there is the only constant, the only harmonic functions on a closed surface are constant. However, this other direction that essentially this condition is sufficient is going to be, there's something highly non-trivial in that. So that's what we're going to talk about next time, the proof of, essentially if you have this, then you can solve this Poisson type equation. But then what I want to do now is to at least give an idea of how to sort of prove this theorem here based on using this theorem. So I'll leave most of this to you as maybe an exercise in making sure you understand things. But let me just prove this map sigma is an isomorphism as claimed. Okay, so maybe just there's a sigma up there. Okay, so let's give a proof that this theorem And this will be a kind of a useful segue into the next topic. Okay, so what's the, if we want to prove it's an isomorphism, we need to prove, I mean, it's clearly complex linear, so it's just enough to prove that it's injective and surjective. So why is it injective? So this is not using the main theorem. Okay, so what does it mean to say that the class omega bar is equal to 0? That just means that omega bar is equal to, right, by definition, it means that it's del bar of some function. Right. But that just means that omega is equal to del of some function f bar, right? But then we know omega is a holomorphic one form, so we know that del bar of omega 0 is equal to 0 is equal to del bar del of f bar. So in other words, the real and imaginary components of f bar are both harmonic. So i.e. the real plus imaginary components of f bar are harmonic. But there are no non-constant harmonic functions on a what am I trying to say? There's no non-constant harmonic functions on a closed surface, and so this means that these guys are, this is constant, so this implies f bar is constant. So this is really, go back here, this is equal to 0, which is what we want to show for injective. Okay, so the next thing to show is that it's surjective. Right, so we're going to start with some class theta over here, and we want to try and get it from a holomorphic one form. So the point is, if we pick any two representatives, so if theta prime is another representative, so theta is 1, then we have that theta is equal to theta prime plus, by definition, del bar of f for some function f. Right. So the point is, we want to try and make if we want to make, say we just pick theta, we're given it, we want to try and make this guy to be such that it's the image of this map sigma. That means that we want theta prime bar, which is equal to theta bar minus del bar of f. Minus del of f to be f bar to be holomorphic, right? So in other words, if we just apply del bar to this, right, that means that, i.e., we want 0 to be equal to del bar of theta bar minus del bar del f bar, right? But the point is, this is exactly, if we rewrite things, this essentially means that we want to write, this is to say, up to, because delta is equal to 2i del bar, this is really the same as right, this is the same as solving, this is essentially the same as solving delta of f bar is equal to 1 over 2i del bar theta bar, right? Right, but of course, we're really sort of saying that we're really. I mean, we want to apply the theorem. We need to, we apply this to the real and the imaginary part, but that's not an issue. But the point is, I mean, to apply the theorem, we need to know this integrates to 0. But of course, this guy integrates to 0 by Stokes' theorem. Right, since this is really equal to 1 over 2 pi I d of theta bar. And so we can just use the theorem to say, find exactly the f bar we want, which is, it won't be unique, but it'll be unique up to addition of a constant. And of course, changing f by constant won't change our function theta prime, right? So the point is now we can just use the main theorem, or the theorem, what did I call it? Use the star to find f, right? Or f, right? And then we're done. Okay. So all the other proofs in this theorem here follow along the similar lines. Okay, so as I said, I mean we're using this theorem here to get some non-trivial information about the relation between these sort of Dolbeault groups and the de Rham group. So our application of this, which will be useful in understanding this uniformization theorem, is that let me keep this. Is now that we're going to use this to find. So one thing this immediately tells us is that there's lots of when the topology is non-trivial, we have lots of holomorphic one forms, right? In fact, we have exactly G linearly independent holomorphic one forms if the genus is G. So yeah, the question that we had this other kind of object we were interested in, which were the meromorphic functions. And as we'll see, it turns out that we can use these ideas to actually give us a proof that we also have a non-trivial number of meromorphic functions, at least if we have enough poles, right? So now we're changing gears to look at the existence of meromorphic functions. So this is the following theorem. So let X be a compact Riemann surface, closed, and let of genus G, and let P1 up to Pg plus 1 be G plus 1 distinct points. Then there exists a meromorphic function map Q that takes X to S2 with simple poles on a subset of the P1. Okay, so what does this mean, right? Notice I want to emphasize this, that we don't ensure that we get a pole at every point. We just get a subset in principle. We can look at the proof and see where exactly we'll see when I give the proof where exactly this comes up. But one thing to observe, of course, is that we need, in general, we seem like we're going to need, in principle, we're going to need at least this G plus 1 points. We know that if X is not S2, we need at least more than 1 point, right? Because if there was only 1 point, then we would have, and we had such a Q, we would have to be on the sphere. But it's actually a bit of an interesting question to try and think about how important it is that we take a subset. Oh, and I should say simple poles, it's a subset and nowhere else. Okay, so our proof is going to use this main theorem, and so let's try and see how this goes. So the idea is actually quite simple, right? So let's just fix a point in x. Say p1 in x, and let's try and think how we could try and find a meromorphic function with a pole at p1. Obviously, we can't actually do this unless x is the Riemann sphere, but let's think about how to try and do it. So we observe that that there exists a neighborhood, a coordinate chart, a holomorphic coordinate chart, U about P1, right? And if we think about it, right, so we have this map U tilde phi, and we let phi of p be equal to 0, then we can define a kind of a meromorphic function, at least in the neighborhood of P1, by just saying Q is equal to phi pull back 1 over z, right? Right. So this gives a meromorphic function on U. And I mean, the question is, how could we extend it to x? Well, obviously we can't extend it to x unless x was the Riemann sphere. But we could, as a holomorphic function, but we could at least try to extend it as a smooth function, right? So the idea is we can extend this as a smooth function to x by taking a psi, which is a C-infinite function of compact support in U, where, say, psi is identically equal to 1 in a neighborhood of U, in a smaller neighborhood of P1, so a smaller neighborhood of P1 than U, and just define a new function which we call, say, Q hat. Let's say this is Q of P. Q hat of P, this is equal to psi times QP, right? So the point is, this of course, because this function is 0 everywhere outside of U, but it now gives us a smooth function on all of x who does have, it's meromorphic in a neighborhood of P with a simple pole exactly at P1 and nowhere else. So the question would be, can we sort of modify this in order to make it holomorphic everywhere away from P? And that's where the main theorem is going to come in, right? So okay, so now let's define A of P, right? So let's define this to be equal to del bar of Q hat of P, right? So observe that this is now a 0, 1. This is a complex valued function. This is a 0, 1 form on x minus P1. P1. Okay? Okay, and in fact, right, if you think about it, right, if you look at how del bar acts, right, so del bar of Q hat P, like near P1, right, this is equal to del bar of psi q of P. Right, so if it hits, I mean, we have a Leibniz rule, so this is del bar psi qp plus psi del bar qp. Right, so here the psi is constant near P1. Right, so this is actually 0 near P1. On the other hand, this guy is a meromorphic function near P1, and so near P1, this guy is 0. This is 0. So actually, the A of P is, so AP1 is actually identically 0 near P1. So we can extend it actually over the point P1. So in fact, so it makes sense. Okay, right. And the point is, if this guy was meromorphic, then that would mean that this was 0, right? But of course, we don't expect that to be the case in general. Okay, but what we could try and do is at least modify it as much as possible to be meromorphic to see what goes wrong, right? So we want to modify this. Modify, say, q hat of P1 to make it, let's say, meromorphic. Okay, so what does that really entail? Right, so notice that this class, I mean, what we want to do is we want to add some nice function to this to make it meromorphic. So one of the observation, as we saw with this previous proof, that if say the class, right, so of A P1 was equal to 0, right, so this is now in this H01, right, then that means that HP1 is equal to del bar of FP1 by definition. Right, and then we see that in fact, if we look at q hat P1 minus FP1, right, then the del bar of this is equal to 0, right? And so this guy is, of course, a smooth function. And so this near P, this doesn't affect anything. Near P1, this doesn't change the sort of singular behavior of q hat. And so this would actually imply that this was this would imply that we had a meromorphic function. Now, of course, right, as we know, if X is not the Riemann sphere, there can't be such a meromorphic function. And so we have to conclude that this in general should not be equal to the identity. But the point is, by what we did before, right, with this theorem, like we actually know how big this space is because it's exactly depends on the genus of G. So the upshot is, right, if we have right, the upshot is now if we take the points P1 up to Pg plus 1, right, we can do exactly the same thing, and now we get these classes AP1 up to APG plus 1, right? But now we have G plus 1 elements inside of a G-dimensional space, right? So these have to be linearly dependent. So there exists a linear dependence between these points, right? So we have lambda 1 right, where the lambda I are not all 0. So these are not all 0. Obviously, it's trivial if you take them all equal to 0. But so then this means that this implies that there exists a function f such that lambda 1 q hat 1 plus lambda g plus 1 q hat g plus 1 plus f. Now this is meromorphic, and the poles are exactly the points where the lambda i's are not 0, right? So if the lambda, I mean, it's possible the lambda could be 0, and then we wouldn't be able to get a pole there. Okay, so that's why this subset shows up. Okay, so that's the proof of the existence of a meromorphic function. And so what this means, just going back to, remember we had this Riemann existence theorem, which said if we had this data on, say, a Riemann surface, we could construct a meromorphic, say on a Riemann sphere, so you had some marked points and some, all this combinatorial data, say on the Riemann sphere, we could construct a Riemann surface. What this says is that actually that construction gives us all closed Riemann surfaces. So this is, in a way, this is one way of thinking about a uniformization, though we'll see maybe a more concrete approach in the next few lectures. Right, so this of course doesn't directly use the main theorem. It uses this theorem here, which I of course erased, but which of course, as I said, uses the main theorem, which is the thing we'll mostly focus on proving. Okay, so then so the final thing I want to talk about now is very briefly use the fact that there exists meromorphic functions to prove a kind of a nice fact about the relationship between genus of Riemann surfaces that admit when you have a branch map between them. And just have a very brief amount of time, so I'll just be very quick, right? Right, so recall right, a meromorphic function, a meromorphic form is an element in H10 of x minus delta, where delta is a discrete, so it's holomorphic away from a discrete set of points, and in a neighborhood of each point of delta, omega, so omega is equal to q of z dz, where q is meromorphic. So of course this so the observation is, of course, I mean, the thing I wanted to sort of mention about this is, first of all, now we know these guys should exist, right? Because we can just take a holomorphic function, which, as long as we're not the sphere, we can show exist, and say a meromorphic function, which we have just been able to construct and multiply them together to get a meromorphic form, and then that works everywhere except for the Riemann sphere. But the Riemann sphere, we can sort of do it by hand. So you should convince yourself of that. So the point about these is because they can be integrated, we have a little bit of extra information that we don't have for meromorphic functions. So the observation is that if we define we take a disk, a small disk about a pole P of omega, so a point where it fails to be smooth, say, right? So, and small enough so there's no other points, then we can define this residue at P of omega as well defined as just the integral over the boundary of the disk of omega, right? So this is some numerical number we can associate to this form, and the point is, right, since this is holomorphic and hence closed, so by Stokes' theorem, so on the one hand, if we have any U, some open C infinite domain in X, that the integral over the boundary of U of omega, so assume there's no poles on the boundary, then this is equal to the sum of the P in U of the residues of P of omega. So this implies, in particular, if you have a closed surface, then the sum of the residues of all the poles is 0 over a meromorphic function. But so that's a kind of global fact. But then observe, you also have the following local fact, which is that right? We've already shown that meromorphic functions or holomorphic forms, right? Locally, the only information you have is the order of vanishing. So of course, the observation about this is that this actually does persist in the local structure. So if omega is a meromorphic form with a pole at a point P, then near P, then there exists a chart such that omega is equal to now z to the n minus n plus a minus 1 over z dz. This is if n is bigger than or equal to 2, or just omega is equal to a minus 1 over z dz. So in other words, I mean, this is just a remark, but right. I mean, it's interesting that, of course, a meromorphic form, you look locally, you have some obstruction to making it trivial, which is the residue. And so this A minus is exactly this residue. Anyway, that's the local theory. But what I wanted to say, which I guess I'm running out of time, but right. So the other thing, which is related to this. We have these existence of various objects. We want to say something about them. So let me just state a theorem, and I wasn't going to prove it anyway. But so if omega is a meromorphic, this is a more global fact, meromorphic one form on a closed Riemann surface X with genus G, then the number of let me just get this sign right. The number of poles, right, minus the number of zeros. No, sorry. Yeah, minus the number of zeros is equal to 2 minus 2g. And here we count with multiplicity. So in other words, look at the order. Right, so this is you've probably, if you've studied this, this has a lot of generalizations. This is a kind of, a prototypical example of like an index theorem. And of course, the proof, which I won't be able to give, but you can prove this using the Poincaré Hopf index theorem. So this is a relation between the topology of a manifold, say, and this notion of index for one forms, for example, or vector fields. But the upshot here is that, of course, this tells us quite a bit about what can happen when we have a fixed genus and the relationship between the zeros and poles. The most important thing is, for example, what you often use this for is to say, suppose I have a holomorphic form, and I know that it has a lot of zeros. So if it has more zeros than this formula tells you it can have, then the only way that can happen is if it is identically zero, a non-trivial. Right, so one observation about this is that if you have a genus 1 surface, then you know by what we did before that the genus 1 surface must have a holomorphic 1 form just because of the computation of the de Rham cohomology. What this tells you is that this holomorphic 1 form cannot have a 0 unless it's identically 0. And so since it doesn't have a 0, what this also tells you is that you can use that non-zero holomorphic 1 form to give a biholomorphism between your genus 1 Riemann surface and the complex plane mod a lattice. So what this theorem, together with what we just did earlier, using the main theorem does is give us a way of proving the uniformization theorem for genus 1 surfaces. In other words, we can prove that every genus 1 Riemann surface has to be a quotient of the complex plane by a lattice using this fact and the previous fact. Similarly, this existence of a meromorphic function, right? If we're a genus 0, then it tells us that by this previous result about the degree, it tells us that the only simply connected closed Riemann surface is the Riemann sphere. Okay, so that's I guess we'll end here, and you should think about these various facts, since I certainly don't.